Welcome everybody to today's video. I was going to do a live stream, but then I decided we're just going to do it as a recording video, just to give me more time to talk, and then also to just honestly just go over the weather and stuff. Now, really interesting here is the reason why I'm doing this as a episode 1 and episode 2 thing is because I found a really good slide from the National Weather Service. It is a few years old, um, and stuff like that, but it goes over both topics. I think it even goes over a little bit in tornado wise. So that's real interesting that wise. And then this also gives me a pointer, so then I can use that to point stuff. But yeah, welcome to the video. Again, this will be posted. This is all free. But it's a nice class and some thunderstorms. They're going to go into depth. We'll also probably at the end, if this thing doesn't go over certain things, we'll go over a little more advanced maybe at the end. Maybe we'll talk about the thunderstorm event that just happened, and then maybe we'll look to see if we have any other thunderstorm events coming up. But this slide is understanding severe storms. You can pull this slide to, if you want to follow along from the National Weather Service. They should have multiple different of these slides. This is the one that I found that is interesting, or at least what I found that covers everything that I want it to cover in more simplified terms. I had another slide before this, but it was not as informative as this one. We're going to go ahead and move along. And topics in this is going to be global circulations. Basically, when we get to that topic, we'll go over more about what global circulations are. Second thing is going to be thunderstorm ingredients. Very important. We're going to be going over to several different types of ingredients for thunderstorms just themselves, and then the ingredients for them to be severe. Lightning is, everybody knows what lightning is, so but we'll go over the different types of lightning. I think that this slide has at least a few different types of lightning, if not most of the types of lightning. Hail. We all know hail can be pretty big. It can cause lots of damage, and sometimes it doesn't cause much damage at all. It can be small hail, but typically when we talk about hail, we talk about severe hail. But we'll also go over how to measure and stuff like that, or if you want to become a spotter in the future, we may do a video on spotting. But for right now, this is going to be kind of mixture of everything. Tornadoes and downburst. Now, I was going to do, I'm still planning on doing a whole separate video on tornadoes, but we'll see how today plays out. If it goes over a very good initial parts of tornadoes, then we might not go much into it. But if the slide doesn't go, I haven't really actually looked into this slide, kind of doing this blinded, but I did get to look at a few slides and I really like it. So, and then we'll be going over flooding. All these thunderstorm hazards, basically, we're going to be going over. All right, global circulation. So, basically, you think of the Earth, it's a big round globe planet. And through your planet, you have high and low pressures, and then you've got the circulations. Low pressure is just a big circulation. So this is very important because, as you can see, you've got your polar jet, which tends to hang up north in the winter. This tends to sag down and give us our winter storms. And then we got our subtropical jet. We've got one that usually stays down here, and then we've got another polar jet down here, as you can see by the globe here. So the North Pole here, and then we've got um, a polar jet that's feeding this cell here, but it's also moving the cell, and this is called a ferrule cell. Not too much familiar with what a feral cell is, I'm guessing it's just a cell by itself. And then you get the subtropical jet. This is what it looked like on a subtropical jet. Um, Storms are able to, it looks, go more higher, and this is a hardly cell. Still not quite sure on that part of it, but that is interesting little graphic there. Thunderstorm ingredients, beautiful. Okay, so moisture preferably in the lower or mid levels of the atmosphere. So when we basically look at a system, especially when we get a lot of these great light systems, we have to look for high pressure here. But then you're also going to have your jet stream or your subtropical jet, whatever you want to call it, the jet stream, anyways. And preferably you want good moisture in the mid and lower levels, just so it gives this storm some nice fuel. The more moisture you have, the more chances of a nice juicy thunderstorm you have with more precipitation. The less moisture you have, the less chance of it being a highly impactful thunderstorm, basically. So you think about it, us humans, we drink water to stay hydrated. Basically, thunderstorms are the same way. They hydrate with water vapor, and if they drink a lot of water, they get big and strong. And if they don't drink any water, they're really dry and they can't perform very well. The upper level jet stream can carry pockets of cold air aloft over moist air, increasing lift and instability. And this slide will be going over more what lift and instability is. But basically, um, when you have your jet stream, which usually flows the direction of the systems towards us, so it basically guides the storms to us, or the storms follow that path. They can kind of go off the path, but technically tend to stay within that path. Lift and instability, basically, instability is energy for that thunderstorm. So basically, um, the heart of a thunderstorm, you need lots of energy or instability to make a thunderstorm. And then you need and then you need even more instability, and different types of instability we'll be going over to make those severe. Low level warm and moist air from the Gulf. So this is again with the warm and moist air. You want that to flow up into, let's say for Michigan, we want that to flow up north. Typically does in the spring and summer months. We see that moisture a lot, which is good for fueling these thunderstorms and severe thunderstorms. Okay, here's some little animations there, kind of explaining thunderstorm development here, or lift. Agent, which source of lift is agent, which lifts the warm moist air starting a thunderstorm. So you're going to see here, you see your cold front kind of coming in. You see our warm air being lifted up, which is causing this cloud, cumulus cloud, to become a cumulonimbus. I can't say it right, but you guys know what I'm talking about here. So you're going to have your cloud here. It's going to raise. It's going to start to tower. When the higher it gets, the stronger the thunderstorm, basically. This is another example here. You can see the warm air kind of hitting this cold air, and it's causing it to slide up and left within here. Another source of lift is instability, ability for air to accelerate upward, downward when started up, down. So yeah, if you think about it, you think of these globes here, lava lamps. You can see them going up and down, and so that's basically your source of lift or instability, is helping those thunderstorms tower up and become stronger. So, like I said, energy for the thunderstorm. So basically, the food. Okay, so these are the thunderstorm's life cycle. So we start at the cumulus stage. Then we get to, so as you can see down here, there's a picture of the cumulus stage. You can see it actually start to tower up as that energy and lift is being provided. So let's just say down here, if we go back, here, you can see that the warm air down here, and then that cold air is pushing the cloud up like that, if you want to think about it simply like that. Okay, so the cumulus stage, warm air is allowing lift and its ability to push the cloud and allowed it to start towering, which we see here as a real life example. Then we hit the mature stage, so the adult stage, pretty much of a thunderstorm. You got your precipitation and cold air coming down here, and then you got your warm air kind of sliding that along that cold area, if you remember. And it is allowing this thunderstorm to tower up and create an anvil here, which usually tops off the thunderstorm. Sometimes, if you can get a really strong thunderstorm, they can produce an overshooting top. So here's a picture of a fully developed mature cell here. Um, this looks like more like a multi-cell, which we'll go over what a multi-cell is here soon. And then you get to the dissipating stage. So this is when the thunderstorm ends the life of its cycle and it starts to dissipate or die off. You get more precipitation. You get the heavier precipitation as the thunderstorm is losing momentum, and this is what it kind of looks like here in a picture of a dissipating thunderstorm. You can see it kind of falling apart there. Okay, here we go. Multi-cell thunderstorm. So you get multiple thunderstorms along this cold front, let's say, or frontal boundary. And you can see that we have, your baby cumulus thunderstorm stage here, and then you can see there's multiple stages, and then you get to the mature stage, which is here, and then dissipating stage. So basically, these thunderstorms tend to last longer in lines and tend to feel a supercell. Um, but yeah, these are why these are able to sustain longer, is that you just have multiple thunderstorms reaching different phases here. Like I said, you got your little phase, and then your maturing stage, and then you got your mature stage, and then you got your dissipating stage here. And it's pretty self-explanatory here. But let's just say there's a cold front here. There's a front providing this all its energy and instability. Typically, when you see multi-cell thunderstorms, they typically tend to be severe. Okay, this explains squall lines. Um, so you get your rising warm air here, which is causing the thunderstorm to develop. You can see your overshooting top here, and then you've got your rain and your colder air that is coming down. This is your downdraft or cross section. So as you can see here, circulating that. Okay, and then we got our supercell thunderstorm here. So you got your downdraft, which we had talked about. This is the cold air releasing from the thunderstorm, or the energy itself releasing. Then, when you have a supercell thunderstorm, you get a mesocyclone. Basically, you see your overshooting top here. This thunderstorm is a very strong, mature thunderstorm. And what you typically see is you get this mesocyclone. So the winds will, as the lift is punching into the cloud, think of it as like a fist punching through a hole through the cloud there. Um, usually the higher it goes and the more shear you have, the winds you have that are also rotating up there will cause this whole storm to rotate, causing a mesocyclone. And then at the bottom of supercells, you usually get the tornadoes. Um, Depending on how strong that mesocyclone is spinning, is depending on how strong your ground tornado will be. Also, you get your precipitation hail through here. This looks more like a high precipitation supercell. There's supercells that are also low precipitation, and then there's low top supercells, different types. Okay, shear versus rotation. So shear, you're kind of just going multiple different ways. So you have maybe wind coming from the south, and then you've got wind going north. You've got multiple different types of wind there. Rotation is spinning. So think of a circle. The winds are spinning to create your mesocyclone. Okay, now we're going on to lightning. That's what lightning looks like. That's a mature thunderstorm or dissipating thunderstorm. This looks more mature, but it's pretty much both. Um, but lightning is pretty. It's one of the most deadliest things of a thunderstorm. So always, when you hear thunder, go indoors. Lightning formation. So as you can see, we've got our positives here, positive electrons, whatever. Um, Usually, when the clouds rising up like this, you have water droplets are starting to move together, slide against each other real fast. There's a lot of motion within the top of that cloud, a lot of energy. and it builds up over time, and then you get these negatives down here, and eventually, once it gets strong enough, it's able to. It wants most electricity. It wants to hit the ground. So it's gonna hit the ground, and you got lightning. So this is one. So you can see your positive, your negative in the cloud here. Then you've got your positives on the ground. And this is number two. You got your negative. You got your positives and your negatives. And then you got your positives going up through the tree, about to connect. Your negatives are coming down to connect with these positives. The lightning wants to reach the ground. Number three, you've got your positives reaching all the way up into with your negatives. It's mixing together. You got your lightning bolt, all the positives all the way down through the tree. Thunder. Um, when the lightning comes down, thunder is the noise or these sound waves coming off from the air being zapped and heated so fast it creates us like a sonic boom. And then us hear it. The closer we are to the lightning, the louder it is. The further you are, it doesn't sound as loud. But trust me, all lightning is loud, especially lightning strikes. Okay, now we're going to be going on to hail. So baseball size hail can do severe damage. So this is what car looks like when it gets hit with baseball size hail. This is what baseball size hail looks like. So you take a, for the measuring instincts, if you take a baseball, put it up against, it's going to look the same. It's going to be around that same size. This hail is also deadly. If you get hit in the head with this hail, it's going to hurt, and it could kill you, or if not, seriously injure you. Hail formation. So you've got your updraft here, you got your warm, again, your warm air kind of riding along that cool air down here. It's your downdraft. Uh, got your rising cloud here, your towering cloud. You typically get hail at the 30,000 feet up in the air there. Usually up here at the top of the cloud, but usually your hail is usually around here. And what tends to happen is when a thunderstorm reaches its mature state, the hail gets heavier once the rain steeps, and then hail starts to fall. Tornadoes and downburst. Here's a picture of a tornado. You can see you've got your supercell thunderstorm here. You've got probably other towers of developing thunderstorms back here. You've got your precipitation right here, your rain, your hail. And then you've got your mesocyclone right here, the spinning section of the cloud, the mesocyclone. And then the mesocyclone, you get strong enough, it reaches all the way to the ground, creates a tornado. And then once you get ground circulation, you've got yourself a tornado. Tornadoes in um, uh, F scale. I'm just going to say that. You've got smaller tornadoes, you've got bigger tornadoes, wedges, different types. Our tornado video, we'll be going over more about tornadoes. So EF1 and not EF, F1 and F0 are winds of 60 to 115 miles an hour. So typically, winds up to 60, that'd be your F0, but most times it's called EF0 now. But your F0s would be 60 miles an hour. And then 60-mile-an-hour plus to 115 miles an hour max would be your F1. Usually your weaker end tornadoes, but 60 mile an hour can do damage, usually with thunderstorms. So any tornado can do damage, but the lower the numbers, the lower the damage. F1s, they do a little more damage, stuff like that. And you got your ef2 and your ef3 range, which is winds 115 plus for f2s, and then you got your 205 miles an hour plus for your ef3. Typically, usually the biggest tornadoes, usually the most typical dangerous ones that we see out there. We don't typically get to 4 and 5 usuallys, but they're possible, and they do happen. And then you got your F4 and F5s, which is winds greater than 205 miles an hour. That is crazy. When we did have a nasty EF4 slash EF5 almost there last year, caused a lot of damage, and there was a couple deaths. So in our tornadoes video, we'll probably go over Some of those tornadoes, especially here for Michigan, damaging wind. Cold air bursts down from the cloud, spreads onto the ground. Contact accelerates on outwash, can reach 150 miles an hour. That is crazy. Tornado like damage. So, this is what I'm saying. Even if you get straight line winds, um, you're still looking at tornado type damage there. So, always good to be in your shelter if you get a thunderstorm that's producing 100 or even 70-mile-an-hour winds. Always make sure you're sheltering, staying away from windows, because hail or trees, branches, and stuff like that can break a window and can go right through you. So here you got your cold air bursts down from the cloud. So you're pretty much your rain and your it's called your downdraft. And when this rain cooled air comes down hard enough, and your hail and stuff, it creates this thing here. Once it contacts the ground, this is going to be your gust front. And if you're near that, or if you get hit by this gust front, usually very strong winds that can cause damage. These could get pretty strong. Spreads on ground. So here's your outburst stage. You got extreme winds here, and as you can see, it's hitting the ground real hard. It's your gust front here. Um, so yeah, nothing to play around with. Accelerates, outwash. So it's cushion stage. So you got your cushion here, and then you've got your cold air, and that's creating your gust front with your extreme winds here. So both sides. Typically, this side usually is the worst, but yeah, any of one of these sides you want to be taking caution when thunderstorms do this phase, which is the most typical severe weather thing that we see every year. Usually, every year we have a thunderstorm that does this. You're typically never safe from these ones. Downburst aircraft. So if you got, I don't really want to go over this, but we'll go over it for the sake of it. Same chart there. You got your rain coming down, and then you've got your gust front there. So your gust front, and if a plane is coming down to land, they could hit this gust front, and it could crash the landing there. So usually planes avoid storms the best they can. If there's going to be severe weather that day, they typically ground flights for at least however long the severe weather lasts, or if they could fly around it, they usually do that. Flooding, flash flooding safety tips. Do not drive across a flooded roadway or low level crossings. I do see people like this guy here, or this truck and this car. They're like, oh, I can drive through this water. Well, typically, when you look at water, you don't actually understand how deep this water is. And if you have nothing really around to kind of give you a feel of how deep it is, you think that your vehicle can make it through. But as soon as that water hits your engine's done, and you stall out, and then your car will start to fill with water. And that could become a whole other issue with flash flooding. Um, which flash flooding does kill people, and typically a lot of these deaths could be prevented, but people, when they see water, they think they can drive through it, especially these truck guys. They're just like, oh, I can drive through that. I'm in a truck, and they don't realize how high that water is, and then their truck's done. So if you don't want to damage your truck or cause a lot of damage, if you see flash flooding or flooding, just drive, take a different road. It's not that hard, people. Um, just take a different road. Don't ever, even if you have the most fanciest truck in the world with a scuba gear or whatever you call those, I still see those stall on videos all the time. So again, trucks are not meant to be going and swimming in water. Their engines were not meant for that. Even if you put a scuba on there, that may protect you from maybe a few more feet of water, but still, it starts getting to your engine. People are stupid and they think that scuba is going to save them, but their engine has cracks in it and stuff, and it's got, you got to have your airflow through there. It's going to get into your engine, anyways. So always, always drive around flooded areas. If your vehicle stalls in high water, leave it and seek higher ground. So yeah, if your vehicle's done, don't try to fix it. Don't try to do anything. Just leave it. Um, Call for help. have someone else drive on a safer area, and then when the water goes down later or stuff, you can have it towed away or um, stuff like that. Because typically, if your vehicle stalls out in water, it's done. You're going to have to cut. It's going to be costly with repairs and all that kind of stuff. Be especially careful at night when it's harder to recognize the dangers of flash flooding. So night, you can't really see. I mean, you can kind of see the shine of water, but you're definitely not going to be able to tell how far that water is. So at night, if there's flooding, I just stay clear of it. Don't ever try to drive through it. There's too many people that do this, and it's kind of funny because I have people around me that do the same thing, and it's just like, dude, just take a different road. There's a bunch of different options, a bunch of different roads. I get feel like you're out in the country and there's not a lot of options, but still, if you can't go one way, go the other way. There's always a way to get somewhere. And here's your famous phrase, turn around, don't drown. And it says click here, but that don't do anything. Acknowledgements. This is the website where you can learn more about the jet stream if you really want to learn about the jet stream. And this is the end of this slideshow. So I hope this slide was useful. Went over the basics of severe thunderstorm development, your multi-cells, your supercells. Here, I'm going to take this slide off here in a second after I get done summarizing this slide. This was a good slide. I wish it had a little more information, but I think it had just enough to kind of basic-wise it. We're going to go over more about supercells here in a minute. I'm going to see if I can find something or a graph or just something. We'll go over more about supercells. Then we'll go over straight line winds, squall lines, deratios. This didn't really go over deratios, so we'll be going over deratios. Just a couple other things that thunderstorms can do or that are hazardous and stuff like that. So we'll just go over more in depth here in a second. So I'm going to go ahead and take this off the screen here. And then once I find it, we will present that. Okay. Sorry for the camera quality. It kind of sucks, but it's all I got right now. So we're going to deal with it. This looks good. Okay, that's supercells. We'll do. Should have had this stuff pulled up. I don't know how I do this every time. So we'll go over. These are each going to be from the National Weather Service, but we'll go over ratios, downdrafts a little more, and then we'll go over. We're going to be going over supercells. All right, let's get. These are not very. These are going to be enough, I think. Even if it's not. So these you can get straight from the National Weather Service. You type in what is a supercell, you'll get this. That's what I did. So if you want to follow along, know that that's this. But hopefully you guys can see this all right. I don't have the pointer no more. So have you ever looked at the sky on May or June day and seen a very tall storm cloud that has an anvil that stretches as far east as you can see? If so, chances are that you've probably seen a supercell thunderstorm. On the thunderstorm spectrum, supercells are the least common type of thunderstorm, but they have high propensities to produce severe weather, including damaging winds, very large hail, and sometimes weaken to violent tornadoes. That what makes the supercell unique from the other thunderstorm types. It is contains deep impression rotating updrafts called mesocyclones. So there again, that mesocyclone I was talking about. The environment is favorable supercell thunderstorms can last for several hours. So yeah, these thunderstorms typically can last, like again, the cell replacement phase. These things can last multiple hours to several hours. So if a supercell is strong enough and has good winds with it, you could be looking at long track supercell, violent tornadoes, stuff like that, which we have seen last year. What ingredients are needed for the development of those supercells? Although supercells require some degree of buoyancy, moderate to strong winds, uh, strong speed, and directional wind shear between the surface and about 2,000 feet is 20,000 feet is the most crucial factor. Wind shear not only creates the mesocyclone, so you need a wind shear to create that mesocyclone, but it also allows the storm to be tilted. So when you think of supercells, they're going to be kind of tilted a little bit. And that's that cold air kind of leaning there, and you got the rising motion here. And then along with that rising motion, you get the winds up in the air, upper levels or lower levels that are spinning like this, and you got your mesocyclone, which then it gets strong enough, tornado, and yeah, which is important for maintaining that separate updraft and downdraft region. A separate updraft and downdraft allows a supercell to be long-lived because it reduces the likelihood too much rain-cooled stable air from the downdraft region will just into the updraft, causing the storm to weaken. So usually, your typical run-of-the-mill thunderstorms, your single-cell thunderstorms, or just multi-cell thunderstorms. Supercell is considered a multi-cell thunderstorm. Your typical one cell thunderstorms, the rain cooled air comes down. As soon as that rain cooled air hits, it hits that storm. Storm does not like too much cold air. It likes a little bit, but not too much. Um, that will weaken and kill the storm off. Supercells, if there's a really strong one and they're able to tilt, you have more of that phase going where you have more clouds lifting. You've got more thunderstorms forming on the backside, and typically that cold air will go like that, and it does not hit the thunderstorm and kill it from the rain cooled air. So rain can kill a thunderstorm. If you're ever wondering what can kill a thunderstorm, rain cooled air, definitely one of the reasons. Or you can get too much shear. If you have too much shear, it can blow the tops off the thunderstorms, which not allow them to become surface based, which we had a problem with the last Vera event, but one did end up rooting itself and became a pretty, uh, I wouldn't say it wasn't deadly, but damaging tornado that when it was in Marshall, Michigan. And we'll talk about that here in maybe the tornado video. I think we'll go over that one. That's more related. Supercells are the most common in the central part of the United States, but they can occur in other regions of the country and other parts of the world. There's also a variety of supercell types, including classic, high precipitation, low precipitation, and even miniature. So, nice thing is there's different types I was talking about. You got your classic supercells, which are just your normal, more photogenic supercells, and you got your high precipitation. High precipitation can be dangerous because if that rotation is close enough to the precipitation, which it usually is, your tornado can get hidden in the rain, and it all looks the same, and you don't know where the tornado is until it's too late. And then you've got your low precipitation. Those are typically nicer to chase if you're a storm chaser, and usually nicer to warn of. Um, but if it's a nighttime tornado, it's going to be even harder to see. But think if you have that high precipitation, you have that rain even at night, it's going to be even more dangerous. So, like I said, tornado watches, tornado warnings. If your area is issued in a tornado warning, always take cover. None of these supercells typically exhibit a textbook appearance on radar and on the field for spotters. Radar features may include the presence of a hook echo, weak echo region, or WER, a bounded weak echo region, a BWER, and a V notch. I know that's a lot of stormy stuff, but we'll go over what that looks like here in a second. Low level storm features are usually visually identified by well defined wall cloud, a rain free base, a near flank downdraft, distinctly separate updraft and downdraft regions. Classic supercells are most commonly found in the Great Plains of the United States and can be relatively isolated. High precipitation HP supercells are less isolated than their classic counterparts and often form in environments of high degree of so the more like I said, that moisture, you get those stronger thunderstorms and weak mid-level relative winds. As a result, the updraft tends to become rain wrapped, which makes it difficult to identify low-level storm features, including log clouds and tornadoes. Low precipitation LP supercells form in environments with low moisture content and strong mid-level storm relative winds. LP supercells usually don't produce much precipitation, but what precipitation they do produce, usually in the form of very large hail. These supercells form an environment with low atmospheric moisture. They're They're not uncommon in the Texas and Oklahoma panhandles. Tornado Alley miniature supercells are smaller versions of classic supercells that typically form in the cool seasons, and they are characterized by weak to moderate buoyancy that is combined to relatively small vertical depth below 2,000 feet above ground level. So here is what your see if I can I don't know if it's gonna work, but we'll see. Okay, that seems to be okay. I hope that's big enough. Okay, so you got your top of your storm here. This is what it looks like on radar. You get your heavy rain and hail in this red area. Usually comes up as pink. You've got your inflow band here. Your updraft, which is feeding the storm here on the radar. You've got your front, your cold front here, which is feeding the storm. And then you've got your flanking line. This is what a classic supercell looks like from the top. Pretty nice there. That's what it kind of looked like on radar and just normal weather stuff. Then you've got your heavy precipitation one. You've got your light rain and outflow, your heavy rain and hail. Um, you have more heavy rain, especially around the hook here, which usually is where your log cloud and tornadoes will be, is on the hook here. You got your cold front, your updrafts, pretty much everything we went through. So these ones are really dangerous to spot tornadoes. It's very hard to see when that happens. Then we've got your low precipitation supercell. Usually these are harder to kind of see on radar just because they're not as vibrant in color. But you usually can still see your updraft, your flanking line, your anvil edge. You got moderate heavy rain, large hail, light rain, and or small hail on the back side. Or no, this could be, I don't know which side is what, but one side has larger hail than the other. Usually more towards that mesocyclone, that's where your larger hail will be. It can be difficult to characterize the type of supercell because it will likely evolve from one type to another during its life cycle. So one could be a classic supercell, then it could go to a high precipitation supercell at HP, and then you got your low P supercell, so it could go through all those phases. For example, a supercell may initially form as a low precipitation supercell on the cap park, but by the time it moves off the cap park, it may transition to its classic supercell. Regardless of the supercell types, the process responsible for supercell formation are the same for every location, so all of these can produce tornadoes. That's your tornadic thunderstorms there. Now we'll be going to hold on, give me a second to pull it up here. It shouldn't take me that long. I already have it pulled up. Okay, now we'll be going over derechos and thunderstorm winds. So here's what a squall line or derecho, same thing, looks like. Usually have your shelf cloud here. These are typically, usually people look at, pretty scared of these, but these typically are not those thunderstorms to produce tornadoes, but if they are strong enough, You can have your QCS tornadoes, which are I talk about in the tornadoes video that we do. When most people think about winds associated with a thunderstorm, they think tornadoes. However, in most years, there have been more damage reports from thunderstorm straight line winds than from tornadoes. Straight line winds are thunderstorm winds that have no rotation, and it's not a tornado. Again, not a tornado. Most people, I've seen people on YouTube see these things and they're like, "Whoa, that's a big tornado. This is just a derecho or straight line wind thunderstorm. These are not tornadoes. They can produce tornadoes, especially if they have supercells embedded with them. But typically, they do not have tornadoes, and they usually do even more damage, usually, sometimes more than tornadoes, just because they're more common than a tornado thunderstorm or a supercell is. Because typically, in order to get your supercells, you need space. These supercell thunderstorms like to be isolated. If there's too many storms nearby, they usually collide and become um, derecho or straight line wind thunderstorm. Straight line wind thunderstorm or a squall line, more typically referenced there. A squall line is pretty much the same thing, but usually squall lines are typically they only last an hour or two. Now, a derecho is a very long-lived and damaging thunderstorm. A storm is classified as a derecho if wind damage losses to more than 240 miles and has winds of gusts of at least 58 miles an hour or greater along most of the length of the storm path. Um, and then downburst, your downburst with your rain and stuff. If you get a strong enough downburst, very strong downburst, they can reach over 100 miles an hour, and then you got your straight line winds there. Here is a picture of the Midwest East. This is the 2012 East Coast derecho. Um, so this kind of started, it formed at 2 p.m. here, kind of stretching into Michigan here, southern Michigan at the tip of that when it started. Gained strength around 4 p.m. In Indiana, and then it continued to gain strength all the way until 12 a.m. when it finally reached the last part, and it was over 600 miles storm. And again, a squall line is a multi-celled thunderstorm, or a derecho is a multi-celled thunderstorm that is able to live for a long period of time. Now they go through replacement cycles of the thunderstorm, so sometimes during its phase it could be a little bit weaker, like 8 p.m. It looked a little bit weaker, but as you can see, they have this bowing shape, like a crossbow or just a normal bow and arrow. You got your bowing shape. Usually, when thunderstorms see this way on radar, they come with very strong winds, and usually on the front of these, you have your gust front. Um, this created wind gust of peak wind gust up to 80 to 100 miles an hour. Millions were without power after that. And then here is a graphic um, of what that looks like, especially with planes. You got your high wind area here and your high wind there, and then no direction, wind direction change. You can have multiple directions and stuff like that. So if we go here, we can see more about derechos. About derechos. Here's a cool art look of what a derecho looks like. Here's another example of a squall line or a derecho. Uh, Here is the definition of a derecho. Derecho, pronounced derecho in English, or pronounced phonetically as a derate something, is a widespread, long-lived windstorm. Derechos are associated with bands of rapidly moving showers or thunderstorms, variously known as boat echoes, squall lines, or lunar convective systems. Although a derecho can produce destruction similar to a tornado, the damage typically occurs in one direction in a relatively straight path. As a result, the term straight line wind damage is sometimes used to describe derecho damage. By definition, if the swath of wind damage exceeds at least 400 miles and about 650 kilometers, is at least 60 miles, about 100 kilometers wide, includes a wind gust of at least 58 miles an hour, 93 kilometers, along with most of its length. and also includes several well-separated 75 miles an hour or greater gusts, the event may be classified as a derecho. The derecho producing convective systems also could contain certain radar observed features, which those bosons showing you, bow echoes, and rare inflow jets discussed on the ratio development. This crowdment was added. This kind of gives you um, why this is the history of where it's got its name. Yeah. Um, so July 4th, 1977. Sorry, something weird happened. I think that might have been a cat. I'm not quite sure. Um, oh, this one actually hit us. More recently, the derecho that swept across Wisconsin and lower Michigan during the early morning of May 31, 1998. If anybody remembers this, please comment below. Measuring wind gusts of 28 miles an hour in eastern Wisconsin, and estimated gust up to 138 miles an hour in lower Michigan. I think this was the ratio, the worst ratio we ever had in history. It was around May 31st, 1998. So as you can see, these storms can last 250 miles an hour to be called a derecho there. Um, this is your casualties. Because the derechos are more common in the warm season, those involved with outdoor activities are easily, especially at risk. Campers or hikers in forested areas are vulnerable to being injured or killed by falling trees, and those at sea risk for injury or drowning from the storm winds and high waves that can overturn boats. Occupants of cars and trucks also vulnerable to falling trees and utility poles. Further, high-profile vehicles such as semi-trailer trucks, buses, and sport utility vehicles may be blown over. At outside events such as fairs and festivals, people may be killed or injured by collapsing tents and flying debris. Even those indoors might be at risk of death and injury. During the ratio, mobile homes in particular may be overturned or destroyed, while barns and similar buildings can collapse. People inside homes, businesses, and schools are sometimes victims of fallen trees and branches that crash through the walls and roofs. They also may be injured by flying glass from broken windows. Finally, structural damage to the building itself, for example, removal of the roof can pose danger to those within. Other reason that those outdoors are especially more vulnerable to derechos is the rapid movement of the parent convective system. Typically, directly producing storm systems move at a speed of 50 miles an hour or greater, and a few have even been clocked at 70 miles an hour. For someone caught outside in such rapid movement means that darkening skies, other visual cues that serve alert to one impending danger. Gus Frank Self-Class, see photos down below. We'll look at those in a minute. Appear on very short notice, and in summary, the advance notice given by the ratio often is not sufficient for one to take protective action. The following links provide those who have survived while being outdoors. Here's another graph of, so yeah, your family of downdraft clusters ratio kind of going over here, microburst down here. The ratio development here. You got your front, gust front. You got your thunderstorm processes here going on here. Your radar description, gust fronts, and updraft there. That's what that picture looks like. And then here's number 2 of that being developed here. That's what it looks like on radar. You can see that bow. That's your gust front. And then here's an even stronger one. Looks even stronger. It's even more bowed. That means you're usually probably going to get 70, 60 mile an hour winds with that. Here's what one looks like on satellite. We'll watch this real quick. You can see your thunderstorms developing here, and you can see that line forming, multi-cell thunderstorms. And That is what a derecho looks like when it forms. So as you can see, it starts off as thunderstorm clusters, and as it moves forward, it becomes more bowed and more thunderstorms get onto it, and then it strengthens as it goes out. Here's more on the heavy raining part of it, uh, ratio moving. Older storms dissipate at the top, cooling parts. Upward system. Pretty much the different parts and stuff that goes into a ratio there. This is typically what the weather pattern uh, usually have progressive, and then you have serial. You get a big high pressure. So usually, like last summer, if you get a high pressure dome here, you're gonna have this your jet stream, and you're gonna have your low pressure here, which is the jet stream is gonna carry this through, and usually comes down, depending on how strong this high pressure is. Will squeeze a thunderstorm through the lower Great Lakes here. This is the progressive pattern. This is usually what we have to. This is what it has to look like for us to get these long-lived straight line wind events, derechos. Um, Typically, if there is the high pressure is lower, but it's still pretty strong wind fields, typically those are more typical for your lower Michigan. So let's say my area to get them. But if the higher pressure is more north, the storm may be more north. Also, another limiting factor of this is usually when the storms cross the lake, it's the lake's cool, still cool by that time. It could cap the storm development, and then the line of storms may come and cause wind damage at the lakeshore. But as it moves inland, it dies and loses energy. But sometimes, if the lake is cool still and these storms are strong enough or developing when they go over the lake, and they hit our warm, moist air and instability, sometimes these storms can naturally re-strengthen and then they become worse, like that Wisconsin one did. So sometimes the lake can actually help or not help them. This is usually your wind direction for your serial phase. Mm. You've got your gust front here, your storm. You got your cold front, your low pressure system here moving this. You got your wind direction going that way. Um, and this your derecho event in this orange here. And then your progressive, usually wind directions going east. So you're going to get most of your derechos that are a little bit longer looking like this. Your gust front here. Typically, these ones are typically your more devastating ones. These are typically the more dangerous versions. And then you've got your progressive, still very strong, but usually these storms are not as big. Now there's hybrid derechos. Occasionally, derechos having characteristics in both serial and progressive events are observed. These events are known as hybrid derechos. For example, the Southern Great Lakes derecho, another Southern Great Lakes one, of 1990, oh no, this was the same one, was attendant to a strong migrating low pressure system. What the hell? What are you doing, cat? Sorry. Strong migrating low pressure system. However, the derechos path associated with both active system had many characteristics of a progressive derecho. Low dew point derechos. Low dew point derechos most often occur late fall and early spring and associated with strong low pressure systems, and are a form of hybrid derecho. On occasion, they may occur during the warming half of the year, especially in drier regions. The Wyoming one, yeah. So as you can see, us we're more typically we tend to see more derechos and more straight line wind events than tornadoes here in Michigan. Our average tornado count is usually 15. We'll go over more of that in the tornado video. This goes over the forecasting. If you guys want to read this, read more about um, the derecho, there's a lot of information. Another picture here, a lot of information to go over. Here's what one looks like on radar. See, you can go over your velocities. So if we ever do severe weather coverage on these, I will show you real-time velocity data. When you get these darker colors or brighter colors, I should say, you've got your very strong gust front here. You can see the bow there. You got your gust front. The winds are very strong within this region, reaching 100 to 130 miles an hour. Got your bow echo here. You got all your thunderstorms feeding this thing. It's like it becomes one monster storm. And usually, kind of like the event we just had, it started out as a bunch of isolated storms or supercells, and then it created a line. And this line came through and put us gusty winds in Grand Rapids. Not very severe though. I think it caused more hail than anything. Um, and then we had at the I'd say down at the end of the storm, a supercell was able to form, and that pushed through Kalamazoo, causing it to go warned for tornadoes. Um, and then it moved out of my area and didn't drop anything. And then as soon as it got to Battle Creek, it dropped a tornado in Marshall. Again, we'll go over more of that on the tornado video. Um, Here you go. Here's another radar view. This is a really good one. You got your MCV, your mesocyclone vortex, basically like a supercell, but a gigantic version. You got your eye like hurricane there. Then you've got your very strong gust front storms here, your derecho here going into Missouri, about to cause a lot of damage there. Um, these are when they're more frequent. So usually we don't see much, 4% chance in January, February, it goes up a little bit to March, we get back down to 4%. April, we start to see an increase, and then May, June, and July, so 3 months, we have pretty significant chances to see one. And then it drops significantly back down in August, still could get some around that time, and then by the time we hit winter and fall, we typically don't see them. Now fall we have seen them, um, but we typically, it's cooler months, the storms don't really like it, so we usually, that does become more rare. So I'd say May, June, and July, definitely be looking out for derechos in your area, especially in Michigan. Now here is a good map that shows you derecho history, or how common a derecho is in the area. And as you can see, Lower Great Lakes has one derecho every year. Typically has one derecho every year. So I I don't think we had one last year. We could have, but I forgot it. I don't think it was as strong, but we did have one last year, I think. This year, I am forecasting that we actually may have a few chances, and I think above average. Um, so we may see two derechos this year, or at least one very powerful one, just on how this year looks for severe weather season wise. Um, Derechos are happening more often because of climate change. Those who want to fight me on that one can, but climate change is really just happening, and these storms are only going to get worse as it keeps happening. Here's your pictures of your, this could be a supercell actually, but these typically what your derechos or straight line wind events are going to look like. You're going to have your gust front here. Um, no, you're going to have your shelf cloud here, and on the back of the shelf cloud, you're going to have your downdraft winds and your rain, hail, your wind. Your gust front's typically going to be all lighting along that this front of the storm. So if you start to see this front here, the shelf cloud, you're already too close. They are nice to take a picture of if you get out and they're slow moving, but they typically cause a lot of damage. As you can see, a lot of these events have happened in Michigan, in the Midwest here. So we are known for derechos. But actually, what's crazy is that if you go further on back into the 1990s, uh, Actually, no, we did have them. Okay. You see a lot of Michigan in here. So the ratios are really common. So this is going to be, that's why I went over it as much as I did and longer, is because these are more common for us Midwest folks here. And these are usually really costly, damaging storms. And that is the end of this. I didn't read it all. If you want to go through and read the whole thing that this great National Weather Service SPC typed up, go ahead. This is on their website here, and yeah. So I hope you guys enjoy this thunderstorm video. Over an hour long of thunderstorm stuff here. I'll leave this up while I'm talking. And I know that um, we typically, usually, the last couple of years, we've been seeing a lot more straight line wind events. So I thought this would be a good topic to go over. Other than that, that is going to be the end of the thunderstorm part. Now, in this video, I want to add on something extra here. Try not to add too much more time because it's going to take forever to upload if I do. I'll probably post it on Facebook and then it'll be posted on YouTube sometime tonight. So you can watch this as a recorded video. It's not live, so I shouldn't be as laggy or have that weird noise and stuff like that. But I want to kind of want to talk to you guys without pulling up more information, is my thoughts on the season ratio wise. And I already kind of said it. I'll probably have a post up at the end of this week, maybe, about it. But I think that our chances for severe weather, at least for this spring and the early parts of summer, depending on how long we're in a neutral phase 4, and it's looking like quite a while, if we don't transition to La Nina faster, typically we have our more active tornado and derecho events during that time. Now, the reason why I'm thinking that we're going to see more derechos this year, or at least one big one this year, is because we're going to be in a progressive pattern at some point. We were in one last year. Um, Fortunately, we got saved from a couple of them, but they did form. A few of them formed last year. I do know that. It was above average form last year. Um, I think one did clip us or came through us, but it wasn't that strong. At least I think Grand Rapids got hit by the hardest of it. Um, we did get damage last year from one or two. But maybe in the future, I'll go over more in-depth derechos, more just Michigan-wise, and what kind of damage we could be looking at through Midwest ratios and stuff like that. Maybe going over what to do if you're outside and one is approaching you faster, and other things like that. But yeah, definitely my thinking is it's going to be more active this year. So definitely be keeping an eye on your weather sources when we get into more spring here. Um, and we've already seen severe weather happen early this year with tornadoes. I think that's going to continue, and I think that's going to ramp up at some point. And I think it's going to ramp up here soon, sooner than later. Now, looking at the long range GFS, I do see some cooler air. So we could have some more snow chances before then. Um, it's not looking really cold, but 30s and 40s may be back for some weeks with warm ups through them. But like I said, with those warm ups like that, if we get like significant warm ups with moisture involved with them, which usually typically are, those are fairly favorable developments also for derechos and straight line wind events and tornadoes in general. So we have to watch these cool downs and when we warm up abruptly. So like if we warm up abruptly from like all the way from 40s all the way back up to the 70s, it's very prime environment for thunderstorms. Again, you need that cold front or cold air, and then you need that warm, moist air for that lift, your instability there. Kind of showing you here in this thunderstorm here. You've got your inflow here, which is feeding the cell, and then you've got your downdraft, which is the rain cooled air coming down with the hail and stuff. But you usually have a front here just pushing the storm. You have something that guides the storm. Fronts usually tick off these storms. So if you get like a strong cold front like we just had, typically get these severe events. So just pay extra attention this year. But that is it for this severe weather week, episode 1 and 2 on thunderstorms. We'll have another one out. I plan on doing that one maybe tomorrow, or having that one up by this weekend. The tornadoes videos will be the last episode for the severe weather week. Um, and we'll probably go over flooding more on the tornado video. We'll go over flooding again. But tornado video is going to be the last one. So I hope you guys enjoyed this 2 episode special, hour long movie or whatever. And I hope you guys enjoyed. Again, you can find this stuff on National Weather Service SPC pages, stuff like that. If you want to read more about specific types of thunderstorms, if you want to look at these graphics even longer, you can pause the video of where we're at, or you can go to their website for a more clearer view and read about. They have, what's nice about this, they have down here at the bottom, they have different types of thunderstorm events that have happened in real time. So like if we click on the Independence Day one, you can see this is where it started at 10 a.m., 100 miles an hour, and then it came through Michigan here. And this will kind of talk about how it happened, what made it happen, your different types of atmospheric things. Lots of information on this page. If you ever want to look back at a severe weather history event in the 1977 time frame when forecasting was not as good, but thank you for those out there that around that time that were able to give early warning of this storm. All right, that is the end of this video. Thanks for watching, guys. Onward Weather out.